Så lad mig alligevel lige få sagt kort, hvad det var for en lille ting, jeg prøvede at finde der. Which I didn't prepare. Let me switch to English now. Thank you. I'm just going to share with you maybe 2 minutes on this little story that I was going to mention. Linked to this multiple MLR thing. No, I'm not going to. Then I'm just going to do it out loud. Fuck. Don't mention Iterum now, right? Iterum and my computer and the IT department, that's not a good combination. So it doesn't work for me, Iterum right now. That's why I use the other one. There is a new paper, short paper in Nature actually from October. I'll send you the link later on. That is talking about crowdsourcing statistical analysis, as it's called, where they are looking into some football data, or in American soccer data, where they have asked 29 different research groups, that means statistical experts, doing the analysis of some major European League data, focusing on whether players' colors of skin makes them have a higher risk of being expelled, getting the red card by referees. That has been speculated, and many people find clear, significant results. That's unfortunately the case. And I have to say, admittedly, I follow soccer myself quite closely, and I have seen many such cases where I've got that idea, so I was not surprised. I've never even thought that there was data to look into that. But the point here is not to dwell on that topic. The point is to find out, if you dig into it, that the 29 research group, all highly skilled stats people, they give you 29 different answers on the same question. Part of the differences is the choice of multiple X's that they take into their model to predict. It's not quantitative here, but it's the probability, it's the risk of getting the red card. It's a nonlinear extension, but anyway, could be handled linearly or nonlinearly. Anyway, so 29 different choices of covariance, as they call it, as X inputs in a multiple model for the relation, and they get 29 different results, of course. There will be a story in Ingeniøren on this Friday, expectedly, on this nature thing, with some very clever comments by a very clever DTU guy in that one. I hope. It's always a bit risky to see what the journalist did to your very, very good comments. Actually, oh my goodness. Oh, here I am. Anyway, never do something unprepared. 4 more points. 4 more points. Not 4 more years, 4 more points. Model validation residual check. We talked about this last time. This is basically a copy. So see this as a recap of last time. We need to think about, also here, if we are to believe the conclusions of the model, some of the confidence intervals, I haven't even, detailed that, but the significance conclusions, we need to think about that the model is okay, right? The only way we can investigate it is by investigating the residuals. What are the assumptions of the model? One assumption is normality, right? And the normality is an assumption for the p-value and everything to be the proper things that we extract, so that the statistics is okay. It's also that the variance is the same all over. Homogeneous variance. Homoscedasticity, if you talk about this in econometrics context. And then it's the linearity of the model, right? That this linear adding up effects, and it's just a linear plane we put in. That's a strong assumption maybe of real life relations. How do we investigate it? This is something you've seen previously. Basically, if we fit a model like this, with the three effects in, the object will already have saved the 111 residuals for us. They are there to look at. It's put into the fit object and it's named by our residuals. It's there. We can have a look. Let's have a look. I should now, since I started all over, make sure that I read in the data again. Let's go down to here, right? I fit the model, I save the fit in a construct like that. What about the normal plot? It doesn't look too bad to me. There could be something maybe here in the left side that I should be worried about. We could, I didn't bring that today, we could do the Wally plot thing again. As you've seen, you remember the Wally plot? That's the thing where you use this mesh package and then you get the 9 plots and you should find Wally, if you can. That is, you should try if you could pick out the odd one. If you cannot, it's probably okay, right? If you can, you may have a problem. I didn't bring that one, but that's of course nice still to use. Then, a classical plot that we did last time also is to plot the model values, that is yi hat. It is also saved in R, it's called fitted values. It's points on the plane for the x's that we put into the model, right? It's the actual plane values. It's saved. We plot the residuals versus that, and we get this point pattern, this cloud. This plot is used residuals versus the predicted. So EI versus YI hat, right? This is used primarily to check the assumption of homogeneous variance, right? We should see a stable pattern. We should not see a trumpet shape. That's the classical and most frequently occurring problem that could hit us. That we could see a trumpet shape. What does a trumpet shape mean? Trumpet shape would be those with high values have high variabilities. And those with small values come with low variabilities. Very naturally occurring phenomenon in many cases. Actually, that's probably why these guys already log transformed these ozone. These ozone values that we are studying are already log transformed because someone already saw that before if I do not do the log transformation, I see a trumpet shape. You could check if you want. I see a trumpet shape in my residuals, so I log transform. They already did that for us, so we don't have to think about it. It looks nice here. Maybe. Nice. We might be able to see some things. And that's the next thing that I want to emphasize even more today, because last time we only had one X. Now I have 3 X's in my model, right? Temperature, wind, and radiation. Now we plot the residuals versus X1, that is residuals versus temperature, residuals versus wind, and residuals versus radiation. And it's complaining because it couldn't fit in the plot in this very small place I had for it. So I'll try again. And then I have the problem to find out where I am. Here we are. Look at that. Residuals versus temperature. Residuals versus wind speed. Residuals versus radiation. What are we looking for here? I am looking for potential nonlinearities. Here is my visual validation of my linearity assumption, that each x1 enters linearly in the explanation of y. So in a way, I should see if I have, I could put in some curves. Doesn't actually look too bad to me, right? Is there a bit of, I'm not sure actually. I shouldn't see something like this. I mean, I shouldn't see clear nonlinear tendencies in these plots. And I have to admit, I don't really see them. Maybe, if I'm looking closely enough, a smooth thing here would help me. Maybe in the wind speed, actually. Maybe there is a tendency to something like this, right? In the wind speed, look at the middle one. That I'm on the top here, I'm going a bit down, and then I go a bit up again. Maybe if I look at the general trend, maybe, right? If I'm looking for problems. I could see, man, at least then, hey, I could check that further on. Yeah, here's plotting the residuals. It's just the slides telling you what I just did, right? So that takes us towards something that we can also handle today, actually. We're going pretty general now. What if, just what if, my concern about the wind relation is a reasonable concern? What if the relation between the log of zone and the wind is not linear, but it's curvilinear somehow, non-linear if you want? And of course, I'm sure you realize, as already doing quite a bit of engineering studies and having all sorts of courses, that nonlinear relations are in a way more the nature than linear relations. Some of our linear models can be very good tools to do things, practical things, to relate things, but they are rarely true underlying models, right? And even